Welcome to the debate. So imagine someone throws a baseball high into the air towards you. To catch it, you theoretically have, well, two choices. You can freeze time, measure the ball's mass, calculate the wind resistance, the gravitational pull, and, solve a complex physics equation to pinpoint the exact landing spot.
Which sounds completely exhausting.
Exactly. Or you can just act like an experienced athlete. Your brain relies entirely on muscle memory. You've seen 1,000 baseballs fly through the air, and you instinctively know exactly where to put your glove without doing a single calculation.
Right. And for over 70 years, global meteorology has essentially been that physicist, right, trying to catch the weather by calculating the math. But today, we are in the middle of a really profound transition. We are moving away from traditional numerical weather prediction, which actually computes the physical laws of the atmosphere, toward artificial intelligence models that rely entirely on the muscle memory of historical data.
Which brings us to the core tension of our discussion today. Does the verified success of these new Chinese AI weather models, systems like Fengwu and Pangu-Weather, signify a definitively superior paradigm shift in meteorology?
Or does their total reliance on pattern recognition and historical data leave humanity dangerously blind to, well, unprecedented climate events?
My position is that AI represents a definitively superior paradigm. It offers unprecedented computational speed and verified accuracy that physics-based models simply cannot scale to achieve. The old way of doing things has hit a hard computational wall, and artificial intelligence is the breakthrough we desperately need to, democratize forecasting.
While the raw computational speed of these AI models is undeniably impressive, speed is not a substitute for understanding physics. AI's fundamental ignorance of atmosphere thermodynamics and its strict reliance on historical data make it inherently vulnerable to erratic, unprecedented weather phenomena. So, in a warming world, AI should remain strictly subordinate to the physical sciences.
Okay, to understand why this shift is not just an upgrade, but a complete revolution, we have to look at the mechanical bottleneck of traditional numerical weather prediction, or NWP. Since the 1950s, the method has essentially been the same.
Yeah, the grid system.
Right. We take the Earth's atmosphere and chop it up into a massive 3D grid. Millions of little boxes stacked from the surface up to the stratosphere. To predict tomorrow's weather, supercomputers have to solve incredibly complex fluid dynamics equations for every single one of those boxes, calculating how air, heat, and moisture transfer from one box to the next, minute by minute.
Which requires a massive amount of supercomputing power.
And it is agonizingly slow. Historically, this method has only improved its reliable forecast horizon by about 1 day per decade. 1 day of extra warning every 10 years.
Well, that's because the atmosphere is a chaotic system. Calculating the true physics of a chaotic system takes immense rigor.
It takes immense compute, and we are running out of it. Now contrast that with the AI revolution, specifically the July 2023 paper in Nature regarding Huawei's Pangu-Weather model. AI doesn't calculate fluid dynamics. It treats the weather like frames in a video.
Right, pattern matching.
Exactly. It looks at a massive dataset of past weather maps and uses deep neural networks to learn how frame A transitions into frame B. The result? Pangu-Weather was proven to be 10,000 times faster than the European Center for Medium-Range Weather Forecasts IFS system, which is basically the global gold standard.
A 10,000-fold speed increase is a staggering engineering achievement, certainly.
But the critical factor is that the accuracy actually improved. In that Nature paper, Pangu-Weather was more precise in critical metrics, specifically the root mean square error of the 500 hectopascal geopotential forecast at a 5-day lead time.
Sure, the 500 hectopascal level.
And that isn't just tech sector marketing, right? The ECMW independently evaluated the model and confirmed that Pangu possessed comparable, if not superior, skill to their own physical models. They even started publishing its forecasts on their own website. We have empirical proof that AI can calculate in 3 seconds what takes our best supercomputers hours without sacrificing precision. It is a legitimate, scalable replacement.
See, replacement is exactly where this narrative becomes dangerous. You brought up the 500 hectopascal geopotential height. which is essentially the mid-level atmospheric steering currents. Yes, AI is phenomenal at mapping those out because broad sweeping atmospheric currents follow highly repetitive historical patterns.
Because they are governed by reoccurring fluid dynamics.
But if you feed an algorithm 40 years of steering currents, it will interpolate the next frame beautifully. The problem is that AI models do not fundamentally understand weather. They do not know what moisture is. They do not know what latent heat release is or how pressure gradients drive wind. They merely recognize historical arrays of numbers. And that lack of physical grounding creates terrifying blind spots.
Blind spots that traditional models also have simply due to grid resolution limits.
But they are fundamentally different types of blind spots. Look at the recent preprint paper published this February, the 2005.16036 paper regarding AI performance on erratic storms. The data clearly shows that AI models struggle profoundly with sudden turning typhoons.
Well, forecasting a sudden turn is notoriously difficult for any model.
But when a storm does something highly unusual, something driven by a sudden, localized thermodynamic shift rather than a broad steering current, the AI fails. It fails because it is searching its database for a historical match that doesn't exist. It lacks the physics to calculate what must happen next, relying instead on what has happened before.
But you are assuming the AI will always be blind to those localized thermodynamic shifts. Let's move from the theoretical limitations into a concrete real-world test. Let's talk about Typhoon Dolphin in August 2026.
Okay.
This was a massive stress test for the Shanghai AI Lab's Fengwu model. 5 days before landfall, while the storm was churning over the open ocean, Fengwu predicted the exact time and location it would strike the Chinese coast. The margin of error was 30 minutes and about 30 kilometers. That is a microscopic margin of error for a 5-day forecast.
It was an exceptionally accurate trajectory forecast for a relatively well-behaved storm.
It was a revelation for the field. According to the published data, Fengwu became the first model to extend skillful forecasts, meaning practically useful predictions, beyond a 10-day horizon, and it beat Google DeepMind's GraphCast in roughly 80% of the evaluated meteorological variables.
GraphCast is impressive, yes, but
We are talking about telling a city of 25 million people exactly when to close their ports and shelter in place, weeks in advance. That is not just tracing a line on a map. That is mastering the atmosphere's patterns.
you are focusing entirely on trajectory, which masks the AI's documented weakness. Dolphin followed a relatively standard track. But what happens when a typhoon interacts with a complex, high-pressure ridge and suddenly stalls, or hooks sharply in a completely new direction?
The AI calculates the new probability based on similar historical ridge interactions.
But when a storm's movement becomes dictated by microscale physics rather than macroscale patterns, physical models hold the ultimate advantage. They're solving the Navier-Stokes equations, the fundamental math governing how fluids move, for that specific, unique moment in time. The AI is just looking at a pixelated image of the atmosphere and concluding, the last 50 times the map looked roughly like this, the storm went left.
That's a bit reductive.
If the laws of physics dictate the storm should go right this time because of a tiny thermal anomaly, the AI is completely blind to it.
I think we need to adjust how we are visualizing this. Think about it like a master chef baking a cake versus a chemist. Traditional models are the chemist. They are calculating the exact molecular reactions of the baking powder, the flour, and the heat. Yes, the chemistry is physically true, but it takes them hours to formulate a single recipe.
And the AI is the chef.
Right, AI is the master chef who just knows instinctively that mixing these specific ingredients at this specific temperature makes a perfect cake. The chef bakes 10,000 perfect cakes a day while the chemist is still, doing the math on the first one.
Okay, but what happens to your master chef when you suddenly change the altitude? What happens when you put them in a kitchen at 10,000 feet?
The cake collapses.
Only if they've never baked at altitude before.
Exactly. Because the chef doesn't actually understand the chemistry of atmospheric pressure on baking powder. They only know their historical kitchen. And that brings us exactly to the intensity problem. Knowing where a storm goes means absolutely nothing if you have no idea how hard it's going to hit.
I wouldn't say it means nothing. Evacuation routes still matter. Let's say your AI chef predicts the exact trajectory of a typhoon, but it predicts a Category 1 when the reality is a rapidly intensifying Category 4. Your evacuation planning is now dangerously inadequate.
Well, the developers themselves, the teams behind Pangu and Fengwu, openly acknowledge that predicting rapid intensification is a current hurdle.
It's not just a hurdle. It is a structural flaw in how machine learning works. Why do these models fail at intensity? Because neural networks are fundamentally designed to minimize error by finding the most statistically likely outcome. When they are faced with predicting a highly erratic, extreme event, the algorithm naturally tends to average out the possibilities.
It smooths the curve.
Yes, it regresses to the mean. A typhoon's intensity is driven by deep convection, latent heat release, and violently complex microphysics at the center of the storm. It is highly nonlinear. The AI optimizes brilliantly for broad, smooth steering currents, but completely misses the extreme thermodynamic reality necessary for comprehensive disaster management.
Oh, come on. Traditional NWP notoriously struggles with rapid intensification too, precisely because those physical equations you are defending are completely bottlenecked by computation. We simply do not have the supercomputing power to run global physical models at a high enough resolution to capture those microphysics perfectly in real time.
True, the resolution is a challenge.
So what do the traditional models do? They use parameterizations, they use mathematical approximations to guess what's happening at the subgrid level, which introduces massive errors anyway.
But those approximations are grounded in thermodynamic laws. They are constrained by the conservation of mass and energy, not just statistical correlations. When a physical model predicts intensity, it does so because the mathematical physics dictate the storm must intensify, not because a similar picture appeared in the year 2012.
We can't let the pursuit of perfect physical simulation prevent us from deploying a vastly more efficient system. And you have to look at the hardware trajectory. We aren't just talking about current AI architectures running on standard GPUs. We are talking about the convergence of AI with next-generation hardware.
You mean quantum?
Yes. Look at the data from the South China Morning Post in April 2026. Chinese researchers demonstrated that a very simple 9-spin quantum system was able to match or beat a 10,000-node classical network at multi-step forecasting tasks. And it did so for less than 1% of the cost of a traditional supercomputing center.
A 9-spin quantum system is a laboratory proof of concept. It is decades away from replacing the ECMWF.
It proves the trajectory of the paradigm shift. AI provides a scalable mathematical architecture. When you merge the neural network framework with quantum technology, you are creating an ecosystem that physics equations running on $100 million classical supercomputers can never match. The raw processing advantage means we can eventually run enough iterations to capture those nonlinear intensity effects you're so worried about.
Sheer computational volume doesn't conjure physical laws out of thin air. You can run an algorithm 1,000,000 times on a quantum computer, but if it fundamentally doesn't understand the conservation of energy, it won't predict unprecedented energy. And that brings us to the absolute critical vulnerability of this entire paradigm: climate change.
Right.
We are living in an era where the historical baseline is completely broken. The oceans are holding unprecedented levels of heat. Atmospheric moisture dynamics are fundamentally shifting.
Which makes fast adaptive forecasting more important than ever.
But it makes historical pattern recognition incredibly dangerous. Take Fuxi, the model developed by Fudan University. It was designed specifically to attempt 18-month forecasts to predict long-term phenomena like El Niño or La Niña.
Which is incredibly ambitious.
It is, but why is an 18-month forecast historically so difficult? Because you are fighting a war between oceanic thermal memory, the slow, massive movement of heat deep in the ocean, and atmospheric chaos. Fuxi attempts to bridge this by mapping long-term historical patterns.
And achieving long-horizon stability is a massive leap forward.
But it fails to generate public and institutional trust. Sun Zi, the CTO of TechWind, articulated this perfectly. If you predict a major, catastrophic climate event a year and a half out using only historical pattern matching, institutions won't believe it. And they frankly shouldn't.
Why not? If the accuracy holds up,
Because if the climate produces a truly unprecedented event, let's say a convergence of atmospheric rivers and ocean thermal domes that has literally never happened in recorded human history, an AI trained on the past cannot predict it. It is structurally impossible for a pattern recognizer to recognize a pattern that has never existed.
the fear of the unknown is potent, I grant you that. But let's apply some rigorous skepticism to the traditional models. Do traditional physics models fare any better when they are overwhelmed by completely novel variables?
Yes, they do.
Do they? When a physical model encounters an ocean temperature 3 degrees hotter than anything ever recorded, its parameterized formulas, which, by the way, were also calibrated using historical observations, often break down completely. They produce wildly divergent, chaotic results.
But they break down according to the laws of physics, which gives human meteorologists a diagnostic trail to understand why the anomaly is occurring. You can look at the output and see exactly where the heat transfer broke the equation. You can't do that with a black box AI model.
But while the human meteorologists are diagnosing the math, the storm is making landfall. Here is where the 10,000-fold speed increase of AI becomes our ultimate weapon against the unprecedented future. Because models like Fengwu and Pangu-Weather are so fast and so incredibly cheap to run, we don't have to rely on just 1 or 2 forecast tracks. We can run massive, rapid ensemble forecasts instantly.
Ensembles are already a standard part of meteorology.
Yes, but traditional ensembles take hours and are limited to maybe 50 variations because of the compute cost. With AI, we can tweak the starting conditions slightly and run thousands of iterations in a matter of seconds. By generating a massive statistical spread instantly, AI allows us to identify the probabilities of novel, low-probability events far faster than a single, slow, physics-based simulation ever could. We can map the edge cases of what is possible in real time, giving emergency planners a full spectrum of risk.
Running 1,000 iterations of a fundamentally non-physical algorithm just gives you 1,000 statistically smooth guesses. It does not give you the physical truth.
It gives a highly probable risk assessment.
If the fundamental training data lacks the thermodynamic ceiling of a rapidly warming ocean, I do not care if you run the ensemble 10,000 times. It will never predict the sudden intensification of a storm to a Category 5 if that energy state space did not exist in its training data. It will just confidently give you 1,000 variations of a Category 3.
The data is constantly being updated, though. These are not static models locked in the 20th century. They assimilate new observational data constantly, and we have to look at the reality on the ground. For countries with massive coastlines exposed to typhoons and vast inland areas prone to extreme flooding, the ability to generate highly accurate 10-day forecasts at a fraction of the cost is not an academic luxury. It is critical survival infrastructure.
Look, no one is arguing that AI shouldn't be used as infrastructure. My argument is that elevating it to a superior paradigm, suggesting it can outright replace the physical sciences, is dangerous hubris.
Well, let me summarize my position, because I think the trajectory of the technology speaks for itself. I readily acknowledge that AI currently has mechanical blind spots, because neural networks regress to the mean, predicting the extreme peaks of storm intensity and anticipating entirely novel thermodynamic anomalies are, genuine challenges.
Very serious ones.
But we cannot let the perfect be the enemy of the revolutionary. The verified accuracy of models like Pangu-Weather and Fengwu, their proven ability to beat the ECMWF's IFS model in key metrics, and their staggering 10,000-fold increase in computational speed make them the definitive future of meteorology. They have taken the forecasting power previously reserved for $100 million supercomputers and democratized it.
And I maintain that while AI has introduced incredibly impressive computational speed, it remains fundamentally blind to the laws of nature. It can trace a beautiful, highly accurate line on a map, but it does not know what a storm actually is. Because AI naturally smooths out extreme data, it struggles to accurately predict rapid intensification. And because it relies entirely on historical data in an era of unprecedented climate shifts, it cannot foresee the truly novel events of a warming world. Therefore, it must remain subordinate to, or at the very best, strictly a complement of, traditional numerical weather prediction. We cannot trust our future strictly to algorithms that only know our past.
Despite our deep disagreement on the hierarchy of these systems, we certainly share a mutual agreement on one undeniable fact. AI models like Fengwu, Pangu, and Fuxi have permanently altered the landscape of global meteorology. The days of solely relying on the slow, meticulous calculations of grid-box fluid dynamics are behind us.
We are in a hybrid era now, and the shared challenge ahead isn't purely technical. It is human. Building institutional and public trust in these systems, particularly for those long-horizon 18-month forecasts mapping out El Niño cycles, is going to require immense transparency into how these models actually arrive at their conclusions.
Absolutely. As the researchers themselves note, the true test of these models doesn't lie in historical validation papers from 2023. The true test lies in the upcoming years of increasingly volatile real-world weather data.
Which brings us back to where we started. Standing in that field, looking up at the sky, trying to figure out where the object is going to land.
Exactly. Are we better off calculating the exact physics of the falling ball or trusting the muscle memory of the athlete who has successfully caught it 1,000,000 times before? As the atmosphere grows more complex and the stakes grow higher, we leave it to you to weigh the trade-offs between staggering computational speed and the absolute certainty of physical laws. Thank you for joining us on The Debate.